Hello again, Geometry. I am so glad that you are so willing to let me do this. Hopefully you are learning just as well as if I was there, understanding that it's nice to be able to ask questions while I'm there, but hopefully this allows me to be gone and we don't lose a lot of time. Okay, so 5.3 yesterday we talked about proofs using congruence, and they were just one-step ideas. Today we're going to do some more proofs, and the big idea here is going to be transitivity. Just a quick little review. Transitivity, if you remember, is if A is equal to B and B is equal to C, then we know that A is equal to C. So we're doing a little more than one step, essentially. Okay, so there's one new idea that we're going to look at. If you're interested in the first written proofs history, here's a little bit about it, and you can read that at your leisure. But like I said, there's one little new piece of information, and I actually talked about this briefly a few chapters ago when we were talking about corresponding angles in parallel lines. I introduced these alternate interior angles as a preview, so we're going to talk about them explicitly. So these are called alternate, so think every other, interior, inside, angles. And your book will abbreviate this AIA. Something to keep in mind, just so that you can remember the name. Alternate is we're alternating on either side of the transversal, which is the line that cuts through the two parallel lines, or any two lines or multiple lines. Interior is inside of the parallels. Again, it could be non-parallels, but to prove anything congruent, we have to have parallels, which you should remember from corresponding angles, but which will be true for this interior angle theorem again. Okay, so we have two lines, and they're going to be cut by a transversal, so this should look a little bit familiar. Okay, and I'm going to number these so we can reference them. So right now I have nothing marked parallel, okay, and that's fine. We'll get into the parallel stuff, but I don't have anything marked parallel yet. So we remember that corresponding angles would be like 3 and 7, 4 and 8, 1 and 5, 2 and 6. And we said if they are parallel, then those pairs are congruent, okay? Alternate interior angles are alternating sides of the transversal and on the inside of the parallels. So the ones on the inside of the parallels would be 3, 4, 5, and 6. And then we want to match up the ones that are on alternating sides of the transversal. So for instance, 3 and 6 would be a pair of alternate interior angles, as well as 4 and 5. Okay, so again, are they alternate interior angles? Yes. But that's all we know about them until we prove something congruent. Okay? So if I were to go ahead and mark these congruent, then I know all the corresponding angle ideas from a couple chapters ago. 3 and 7 are congruent, 4 and 8 are congruent, 2 and 6, 1 and 5. But now, the alternate interior angles theorem tells us if we have parallel lines, then alternate interior angles are congruent. And of course we can write that in the reverse order as well. If alternate interior angles are congruent, then the lines are parallel. So if you remember kind of the way the book writes this, if we have parallel lines, alternate interior angles are congruent. They usually put that little arrow in there, but that's fine. So that's one way. We have the parallel lines first, and then alternate interior angles congruent. Or the reverse of the biconditional would be if I have alternate interior angles congruent, then my parallel lines, then I know my lines are parallel. Okay, so those are the two ways that we could have that. Again, this is the given. If we were writing a proof, this would be what I'm trying to prove. Here would be my given, and this would be what I'm trying to prove. So just keep the order in mind when we have biconditionals like that. Okay, so let's go ahead and look at example 1, see if we can recognize how to use this. Alright, in the figure at the left, which you can't see right now, there you go. N is parallel to P, okay? So I know that, we have it marked. If measure of angle 3 is 43, find the measures of angles 1 and 2. Okay, so I'm looking over here, I know 3 is 43. So from what we learned just now, what do I know that angle 2 is? Well, I would know that angle 2 is also 43 because they're alternate interior angles. Okay, and then I could figure out what angle 1 is. Notice that 2 and 1 form a linear pair, or they form a straight line. So we would do 180 minus 43 to find angle 1. Ta-da! We were correct. Okay, I do want to take a look at this proof up above that helps us get to the alternate interior angle theorem, okay, so that we can understand why this is a proof using transitivity. So we're just going to read through this. Given that M is parallel to N with angles numbered in the diagram at the right, okay, so this is what we're taking, we know this. Sorry, my video stopped for a little bit. So I don't know if you missed anything, but what I was saying was we are going to look at this proof a little bit, okay? So really quick again, M is parallel to N, because it's in my given. Angles are numbered as so, okay? And I want to prove that 4 and 6 are congruent, okay? And if we had this theorem, that would be our reasoning. But what we're doing here in this proof is proving where this theorem came from. So when we're proving a theorem, we can't use the theorem in it. So this is the whole point of geometry, where we build up from the ground up, and then once we get it, we can use it. So this is where the AIA congruency theorem comes from. Okay, so here's this proof diagram that I showed you yesterday. Okay, M is parallel to N. Great, I know that. It's given. Okay, then this conclusion that somebody made, or that the book is telling us was made, was that 6 and 2 are congruent. How do we know that 6 and 2 are congruent? Hopefully you're thinking right now, well, corresponding angles. If I have parallel lines, then corresponding angles are congruent. Okay, so that would be my justification there. Okay, then 2 and 4 are congruent. How do I know that 2 and 4 are congruent? And hopefully your memory is remembering that 2 and 4 are vertical angles. So the reason or justification of 2 and 4 is that vertical angles are congruent. Okay, so I'm just going to draw lightly in my book so you can see all this. I have marked 6 and 2 congruent, and right now I said that 2 and 4 are congruent. Well, if you notice, what are we trying to prove? I was trying to prove that 4 and 6 were congruent. Well, my picture is showing me that I did. Okay, so this is what I'm trying to prove. Well, what is this reason here? What is this reason? Well, let's go back and read this. 6 congruent to 2, 2 congruent to 4, so 6 is congruent to 4. What's that reason? Transitivity of congruence, right? So that's why this section is entitled Proofs Using Transitivity. Okay? let's look at example 2. Okay. Prove that if we have alternating interior angles congruent, then I have parallel lines. Okay, we want to prove that part of the theorem using this drawing. So again, we're going to look at a proof of transitivity just like what we looked at. Again, we can't use the theorem yet since we're trying to prove it, but once you get to your homework, by all means, use it. Okay. First, write what is given as what to be proved. Okay, so remember this is my 0 step, and this is what I'm trying to prove. Okay, so here would be our argument. 4 and 6 are congruent. That's my given. Okay, like in the picture up here. Okay, so then what they go on and tell us is that, well, 2 and 4 would be congruent. And we know, like just the last one we did, that's the vertical angles theorem. Okay, so I'm going to draw that in my book here. Okay, and I'm trying to prove that 2 and 6 are congruent. Okay, this is again the transitivity. 4 and 6, 2 and 4, so 2 and 6 must be congruent, transitivity property. Okay, therefore M and N must be parallel. Well, how do I know that M and N are parallel? Well, hopefully you picked up that, oh, 2 and 6. That's corresponding angles from, a couple chapters ago when we had that biconditional as well, that if I have corresponding angles congruent, then the lines are parallel, which is exactly this reason, okay? So those two proofs that we just looked at were proving the two parts of the biconditional of the alternate interior angle theorem. Okay, so it's just kind of giving you some exposure to what proofs look like. Alright, I am going to now do number 15 of your homework with you. Okay, so if you need to pause the video and get your homework out, that's fine, but I'm going to do number 15, or you could do it in your notes, but this is number 15 from your homework. Okay, so like I said, pause the video if you need to. Alright, so 15, use the diagram below and complete the proof by writing the argument. Okay, so what we need to do, I'm going to copy that diagram. Okay, and then my given goes in my 0 step, so B is the midpoint of AC. C is midpoint of BD. Okay, so this is what I have. So I need a justification for this. How do I know all this? It was given. So when we do proofs, hopefully all of you can at least get that part right, which I have no doubt you will. Alright, so let's think about what I know. So first of all, let's make sure we understand what we're trying to prove. I'm trying to prove that AB is congruent to CD. Okay, so I'm going to go up and put some markings in my picture. If B is the midpoint of AC, I know that AB and BC are congruent. If C is the midpoint of BD, well, I also know that CD and BC would be congruent. Well, by the looks of my picture, I have everything I need because I'm trying to show that AB and CD are congruent, which I've already marked in my picture. So what allowed me to put these marks in there and get there, okay? So those marks that I put in were AB is congruent to BC, right? I put that mark in there. I also put the mark that BC is congruent to CD. Okay? Why am I allowed to do that? Remember, the definition of midpoint tells us that the two parts are equal. Okay? Okay, remember we're using transitivity in this section. So I'm seeing AB is congruent to BC, BC is congruent to CD, so I think AB and CD are congruent, which is what I'm trying to prove. So yay, I got to what I need. And what is the reason that I can say this? Transitivity to the D of congruence. And there's your proof. So there's your first proof that you've had to write. Alright? One homework problem done. Awesome. Hopefully I'll get to see you tomorrow. Bye.